Good day everyone, my name is Arcenue and with my partner Trisha Biñas, we will discuss the chapter 16, Cosmologies. So first, I will discuss the subtopic which is first the structure of the universe, second is the Einstein's general theory of relativity, and third is the Big Bang theory, and fourth the steady state theory. So let's start the discussion. So first, I will discuss what is cosmology. So cosmology is a study of the universe, how it began and how it structured, how it changes, and what may happen to it in the future. It includes studying ideas and theories such as the Big Bang theory, which explain how the universe started, and also the theory of relativity developed by Albert Einstein, which helps scientists understand gravity and spaces. So cosmology is a science that studies the origins, structures, and revolutions and futures of the universe. I will discuss the structures of the universe. The universe is a very large and made up of many objects like stars, planets, galaxies, and dust, and also gas. These objects are not randomly placed, they are organized into groups. A galaxy is a large group of stars, and many galaxies form clusters and superclusters. So here is the hierarchy. First is the solar system and stars. At the most basic level, gravity binds planets, moons, and asteroids to the stars. Our solar system is just one of the billion in our galaxy. So number two is galaxy. Stars does not float randomly, that they clump together into galaxies like our Milky Way. This contains hundreds of billion stars along with gas, dust, and dark matter. Number three is group of cluster. Galaxies hang out in neighborhoods. Group first is group small collections like our local group, which includes the Milky Way and Andromeda. And the next is clusters, massive cities of hundreds of thousands of galaxies bound together by gravity. Number four is superclusters. They are the continents of the universe, massive collections of galaxy clusters. We live in the Lenickey supercluster. Number five is the cosmic wave. One on the largest possible scale, the universe looks like a giant superwave. So first is pyramids, time strains of galaxy and dark matter. Number two is points, giant empty space between the pyramids. So next is tubes, the intersections where pyramids meet, usually home to massive supercluster. And the sixth is the blue, dark matter, invisible scaffolding that provides the gravity to hold these structures together, and also dark energy, the mysterious force pushing every apart, causing the universe expansions to speed up. So Einstein's general theory of relativity. So the general theory of relativity was developed by Albert Einstein in 1915. This theory explained how gravity works into the universe. So before this theory, people believed gravity was just a force pulling objects together. Einstein explained that massive objects bend space and time, and that bending causes gravity. So here are another explanations of the general theory of Albert Einstein. So, space-time. Einstein said that space and time are connected together. They form something called space-time where everything in the universe exists. Second, gravity. Gravity is not just a pulling force, it happens because big objects like stars and planets bend or curve space-time. Smaller objects move along the curve created by the bigger objects. So the next is time dilations. Gravity can affect time. When gravity is strong, time moves slower For example, time on Earth moves a little slower than in space. The next is light bending. Gravity can also bend light. When light passes near a very large object, its path curves. This helps astronomers observe very far galaxies. And the last is expansions of the universe. Einstein's theory helps scientists understand that the universe is expanding, which supports the Big Bang theory. So, Einstein's theory explained that gravity helps because massive objects bend space and time, and this bending affects how objects slide and even time moves in the universe. So the number three subtopic is the Big Bang Theory. So the Big Bang Theory is the leading scientific explanation for how the universe began and evolved over approximately 13.8 billion years, rather than a conventional explosion in space. It describes the rapid expansions of space itself from an infinitely hot dense state. So here are the core principles. The singularity universe originated from a point of near infinite density and temperature called singularity. Next is expansions and cooling. Since its birth, the universe has been continuous stretching and cooling, allowing matter to form and eventually cluster into stars and galaxies. The next is cosmic inflation. In this first trillions of the seconds, the universe underwent an ex- exponential growth spurt, expanding faster than the speed of light. The next is the four pillars of evidence. Scientists support a theory based on four key observations pillars. So first is the Hubble's law or redshift. Observations show that distant galaxies are moving away from us the speed proportional their distance, proving the universe is expanded. Number two is cosmic microwave backgrounds or CMB. This afterglow is a faint home of radiation left over from when the universe first became transparent through 380,000 years about the Big Bang. So number three is the abundance of life's elements. The specific ratios of hydrogen and helium in the cosmos match the predictions of what would have formed in the intense heat of early universe. So the last is number four, galactic evolutions. Looking deep into the space allow astronomers to see galaxies as they were billions of years ago confirmed that the universe has changed over time. Here are the timeline of cosmic events. So first is 0 and 1 seconds. Force of nature, gravity, electromagnetics becomes distinct subatomic particles like quarks and electrons form. Second is 3 to 20 minutes. Nucleosynthesis occurs as protons and neutrons fuse the create the first atomic nuclei. The third is 380,000 years. Recombining take place. Electrons pair with the nuclei to form neutral atoms, clearing the cosmic fog and releasing the light when you see as the CMB. So the last is the second to the last is 50 to 500 million years. The gravity pulls gas clouds together to ignite the first stars and galaxy. So the last is 9 billion years. So number four is the steady state theory. The theory was primarily introduced in 1948 by three notable scientists, Sir Fred Hoyle, a first critic of the Big Bang, a term he actually coined as a derisive nickname. Herman Bondi and Thomas Gold, who are inspired by the circular structures of the 1945 horror film Dead of the Night. So, here are the key concepts of the steady state theory. First is constant density. While space expands, new matter fills the gaps, ensuring the density of the universe remains unchanging over time. So the next is perfect cosmological principle. This principle states that the universe looks the same from any location and at any time. Homogeneous and isotropic is both space and time. Next is no beginning or end. Unlike the Big Bang theory, this model proposes an eternal universe. Next is the continuous creation. Matter is created continuously to form new star and galaxy, replacing old distant ones. So that's all my parts for these discussions. So the next topic will discuss by Trisha Marie Biñas.
Thank you, Julie, for that detailed look at the earlier stages of our cosmic history. Now, to continue our exploration of Chapter 16, I'll be taking us through the specific evidence and the models that define our universe birth, growth, and eventual destiny. Before we dive into the details, look at this roadmap. At the top left, the yellow question mark is the Big Bang singularity. The first small oval is inflation, the rapid growth spurt. The middle blue and green mottled oval is the CMB at 380,000 years, which is our first clear look at the cosmos. And then the bottom shows our complex universe today at 13.8 billion years. This image is the photo album of our entire history. So let's move to the primordial background radiation or the CMB. Let's start by looking at this colorful map. It might look like just a bunch of dots, but this is actually the baby picture of our universe. It shows the very first light that was finally able to travel through space roughly 380,000 years after the Big Bang. Before this moment, the universe was too hot and thick for light to move. Like a very dense fog, this map shows us the tiny seeds of heat that eventually grew into the galaxies we see today. Now let's look closer at why this is so important for scientists. This faint glow is the most important proof we have that the Big Bang actually happened. Think of it like a smoking gun at a crime scene. Originally, the universe was incredibly hot, about 3000 Kelvin. But as the universe stretched out over billions of years, that heat cooled down. Today, it is a very cold 2.73 Kelvin. We need special satellites like Planck and WMAP just to detect it because it's invisible to our eyes. Since we know how it started, we have to ask, where is it all going? Now let's move to the future of the cosmos. This graph represents a cosmic tug-of-war. On one side, you have gravity trying to pull everything back together. On the other side, you have the dark energy, a mysterious force that is pushing everything apart. The lines you see here show different theories. Will we expand forever, or will gravity eventually win and pull us back? To simplify these theories, let's look at the three most famous possibilities for the end of the world. First, the Big Freeze. This is the most likely end where the universe keeps growing until it's so big that stars run out of fuel and everything turns cold. Then there's the Big Rip, where the dark energy gets so strong it tears planets and even atoms apart. And the Big Crunch is the opposite of the Big Bang. where everything collapses back into a single point. To understand why the universe is so big now, we have to look at this very first second. Let's jump back to the moment of inflation. Look at how the chart suddenly widens. Inflation was a massive growth spurt. In a tiny fraction of a second, faster than you can blink, the universe grew from the size of an atom to something bigger than a galaxy. This explains why space looks so flat and huge today instead of being a messy, curved shape. You might ask, what caused this? That's where grand unified theories come in. Scientists believe that in the extreme heat of the early universe, the forces of nature were all combined into one superforce. When these forces separated, it released a massive amount of energy, like a spring being let go. This energy is what triggered that growth spurt, ensuring that matter was spread out evenly so that stars could eventually form. All of these lead us to the big question: how long has this story been playing out? Moving on to the cosmic timeline, it took 13.8 billion years for us to get here. For the first few 100 million years, the universe was in the dark ages with no stars. Then the first stars lit up, galaxies formed, and only about 4.6 billion years ago did our own sun and earth appear. We are actually very new character in a very old story. The age of the universe. The universe is approximately 13.8 billion years old. This age is determined by measuring the cosmic microwave background, the afterglow of the Big Bang, and calculating the universe. Most measurements consistently place the age between 13.7 and 13.8 billion years. So let's look at how we are so sure about that 13.8 billion year number. Scientists don't just guess, they use two main methods. First, they measure the Hubble constant, which is the speed at which galaxies are moving away from us, like rewinding a video to see when it started. Second, they look for the oldest star in the sky. Since a child can't be older than their parents, the universe must be at least as old as the oldest star we can find. To wrap up, let's look at the key details of how we calculate the age of the universe. Astronomers don't just guess, they use the Hubble constant to measure how fast the universe is expanding and identifying the oldest stars to set a minimum age limit. Leading the data from the Planck mission suggests an age of 13.82 billion years, while other measurements from the Atacama telescope suggest 13.77 billion. While some alternative theories exist, the 13.8 billion year figure is the widely accepted standard in modern cosmology. To summarize everything up, let's look at the four main chapters of our universe story. The fast start. It all began 13 billion years ago with inflation, a massive growth spurt that made the universe huge in just a fraction of a second. The first light. 380,000 years later, the universe finally turned on the lights. We can still see this today as the CMB, the oldest baby picture of our cosmos. The growing years, over billions of years, gravity took over, pulling matter together to build the first star, then galaxies, and eventually our own home, Earth. The endless end. Today, the universe is still stretching out. Most scientists believe it will eventually end in a big freeze, becoming incredibly large, dark, and cold. Understanding these stages help us see that we aren't just in the universe. We are a part of a 13 billion year old story that is still unfolding. In conclusion, chapter 16 teaches us that the universe is a vast, evolving system that began 13.8 billion years ago with a Big Bang, governed by the laws of Einstein's general relativity. The cosmos moved from a moment of rapid inflation to the formation of the complex, large-scale structures we see today. While early ideas like the steady-state theory suggested a universe with no beginning, the discovery of primordial background radiation or the CMB provided the smoking gun evidence that our universe has a distinct history. By understanding the age and expansion rate of the cosmos, we can predict its ultimate fate, which most likely points toward a big freeze, a future where the universe continues to expand until it becomes cold, dark, and silent.